with video. All right. So,
is it recording?
I think it is, yeah. Okay, so let's see. I'll try to put the new homework assignment up on the web page tonight or tomorrow. It'll probably be do the rest of the problems in chapter 1, but maybe that's too much, so I'll just maybe do the next 9. Anyway, that'll be roughly what it will be. There are crackers floating around the room somewhere. Help yourselves. Are there any questions? Yeah. All right. There's a problem session at 7, and you're all welcome to come to the problem session whether you're signed up for it or not. I have a demo here that I'll show you at some point when you've had a dose of logic that's sufficiently wearying that you need a break. And I'll do the demo during that break. Okay, now, whoa, I forgot to bring my notes. I'll be here in Okay, so I'm sorry about that. I printed it out and forgot to pick it up. So we were talking last time, as I recall, about the eigenvalues of the square matrix. That's more or less where we stopped, right? Is that right? All right. Well, I'll assume so. I think that's true. So suppose A is an n by n matrix with complex entries aik. Now, an n-dimensional vector V will be an eigenvector with eigenvalue A if we have this relation. And in terms of components, it's with A on V, V now being the vector with components of some particular basis that represents this vector. That will look like that, or in matrix, that's in matrix notation. And in terms of components, it will be the sum aik vk, k equals 1 to n, equals a times v sub I. So that's what we mean by an n by n matrix having an eigenvector v with eigenvalue a. This matrix A has no special properties, it's just square and complex, so we don't know a great deal about the eigenvalues. However, we can prove a theorem, namely that every n by n matrix has n eigenvectors V, I'll write them this way, V sub L, and eigenvalues A sub L, and there in fact are n of them, where L goes from 1 to up to n. And in order to see why, we can rewrite this equation in the form sum k equals 1 to n, ki k minus a sub L delta ik vk equals 0. Now, what we want to do is we want to visualize this as a statement of the linear dependence of the columns of this matrix being A minus A sub L times the n by n identity matrix V equals 0. So in other words, the matrix form of this expression is A minus A sub L I on V is 0. And what that's telling us then is that these coefficients Vk are coefficients such that these the columns of this matrix multiplied by the Vk's add up to 0. That means that the columns of this matrix are linearly dependent. At least if we can find a non-trivial eigenvector V, that is to say an eigenvector such that the components of V are not all 0 in the trivial case. So is that clear? In other words, we're looking at this matrix, we're looking at the columns, and we see that the columns of this, each column, the first column gets multiplied by V1, the eighth column by Vk, the nth column by V sub n, and those columns multiplied by the V's have to add up to 0 if this is an if V is an eigenvector with eigenvalue A sub L of this matrix A. Okay. But on the other hand, we've analyzed this in the past, namely the columns of a matrix are linearly dependent if and only if the determinant of the matrix is 0. So that means that the determinant of the matrix A minus A sub L I has to be 0. And well, what is that? Well, that's an n by n matrix, and so its determinant is going to involve at most n powers of A sub L. Okay? So in other words, this equation is the same thing as what we can call, what is called, in fact, the characteristic equation and that is minus 1 to the n, A sub L to the n, plus dot 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 plus just the determinant of A. So this is the other notation, this determinant. Okay. The reason why you know this term must be present is that the term is that if you set all the ALs equal to 0, then this equation would just be determinant of A. So that determinant has to occur. And that's the term that has no powers of A sub L. So this is a polynomial equation of order n or nth degree in A sub L. But there's a theorem which we'll prove when we get to complex variable theory, if we ever finish linear algebra. And that theorem is that any polynomial equation with complex coefficients has, in fact, if it's of nth order, and it has n roots somewhere in the complex plane. And so another way of writing this, of course, is to say sum k equals 1 to n ck AL to the K. So it's a polynomial equation in A sub L, and setting this equal to 0, we know we have that there exist capital N roots A sub L. Somewhere they're complex numbers. We'll prove that theorem, as I said, in the chapter on complex variable theory. And so we know we can find n solutions of this equation. And for each one of them, then, the columns of this matrix, A minus A sub Li, are linearly dependent. And that means that we can find non-zero numbers B sub K. They don't all have to be non-zero, but some of them have to be non-zero, such that B sub 1 times column 1, B sub 2, column 2, and so forth, added up gives you 0. All right, I hope that that's more or less clear. In other words, this equation has these roots. For each root, the determined boundaries. The determined boundaries is the columns are linearly dependent. Columns linearly dependent means we have an eigenvector, a non-zero eigenvector with A sub L as the eigenvector. So is that okay? Any question? All right. Now, in general, this is the normal case. The normal case is that these roots are all different. Not always all different, but typically they're all different. There has to be some symmetry, something special about the matrix A to have two or more of the roots be the same. That is to say, two or more of the eigenvalues be the same. What I want to show now is that if the roots, also known as, or the eigenvalues, A sub L, are all different, then the eigenvectors BL, I don't need a K here, B sub L are linearly independent. Oh boy, linearly independent. Okay, so this is the typical case, namely that the eigenvalues are different. When they are, the eigenvectors have to be linearly independent. In order to show this, I assume the contrary and assume that there are, in fact, some coefficients, C sub L, B sub L, L equals 1 to n, that are 0. So we're assuming the contrary, that is to say, linearly dependent. Well, in that case, we get this equation from the left with the kth power of the matrix A. And that has to be 0 because this sum is 0. But this gives us a sum, C sub L, A to the K, the Lth eigenvector, L equals 1 to big N, and so we have the relation 0 is equal to the sum L equals 1 to N, C sub L, A on well, let's see, I should have written this equation here. A BL equals KL. Somehow I should have written that down. I don't know why I forgot it. Consequently, if we do this K times, then we have A to the K on VL is equal to AL to the K power VL. And so A to the K on V sub L is AL to the K power V sub L. Okay, well, that is saying that this is sort of a linear dependence relation. It's not one, but it's an infinite number of linear dependence relations. And in fact, if we take the inner product of this vector equation with some vector d, then we get 0 is the sum L equals 1 to big N, C sub L, A sub L to the K, the inner product of d with the vector V sub VL, the L eigenvector of matrix A. Okay, well, we can define, let me define some vectors, d k with Lth component being simply AL to the K, the inner product of d with V sub L. Then this vector equation is 0 is equal to the inner product, well, it's sum C sub L, D sub L, K, L equals 1 to N, or effectively it's the dot product of C, or if you want C dot DL of K. I'm sorry, C dot D of K is 0. And or if we wanted to, I could have used C star on the C's, and then I would have an adjoint here, and so it would look like a normal inner product. In any event, what this is saying effectively is that the coefficient C form a vector that's orthogonal to the vector dk for k equals 0, 1, 2, up to infinity, because there are an infinite number of these vectors dk, and they depend on k by having k sub L raised to the k power. Now the point is that if the eigenvalues are all different, then these vectors d are all different. Okay? Because you have these numbers, if they're different, and you raise them to 0, first, second, third power, then they grow at different rates. If some are negative, they change sign. If they're complex, they go bouncing around in the complex plane, and so forth. So these vectors are all different if the eigenvalues are all different. But that would mean that this vector C is orthogonal to an infinite set of n-dimensional vectors. And that's, of course, absurd, because of different n-dimensional vectors. And so the conclusion then is that the original supposition, namely that these were linearly dependent, is wrong, and they're in fact linearly independent. So, all right, so that's basically the idea. Any questions? The point here is that you don't need, to get a contradiction, you don't need that there are infinitely many vectors. It's rather that if the ALs are all different, then these are an infinite number of these vectors are going to be linearly independent, and C can't be orthogonal to all of them. All right, so that's basically the argument. We need some fine-tuning, certainly need some clarity. Anyway, so the bottom line then is, if you have a square matrix, complex or whatever, it will have n eigenvectors and n eigenvalues. If the eigenvalues are all different, the n eigenvectors are linearly independent. And if they're linearly independent, then you can form an orthonormal. You can form an orthonormal basis from these eigenvectors in this span of space. On the other hand, when they're degenerate, when the eigenvalues are degenerate, which is a special case, when the eigenvalues are degenerate, then you can't be sure whether the eigenvectors are linearly independent or not. And there's in fact the situation is if the eigenvalues, if the eigenvectors, as I should say, are not linearly independent, then the matrix is said to be defective. So the normal case is that the matrix has n orthogonal and different n eigenvalues. They're all different. In that case, it has a linearly independent set of eigenvectors. In the special case in which there's some degeneracy of the eigenvalues, some of the eigenvalues are equal, then you're not sure whether they're linearly independent or not, the eigenvectors. And if they're not, the thing is said to be defective. Yeah.
I guess if you've got two linearly dependent eigenvectors with the same eigenvalue, how can you tell that they're two eigenvectors?
Well, I mean, you just have two vectors that are eigenvectors with the same eigenvalue, and they're different eigenvectors. But as you say, if they're linearly dependent, and there are only two of them, then they have to be proportional. And so you can, if you want, say, in fact, you only have effectively one. And so that's possible. That's a good question. All right, so let's see, where were we? Okay, so obviously we're not going to work very much with defective matrices. So a defective matrix is one whose eigenvectors aren't linearly dependent. All right, so suppose we have a non-defective. Suppose A is n by n, and it's not defective. Non-defective. In other words, its eigenvectors are linearly independent. Then we can use its eigenvectors d sub L, or equivalently call these simply L, to define the columns of an n by n matrix S. And in other words, the columns SKL might be the inner product of some basis with the eigenvectors of the non-defective matrix A. And these vectors K, the ones I chose here, are the ones in which AIK is I0, A, K0. So in other words, we're representing the linear operator A by this matrix square Aij, and the basis that gives us this matrix to represent that operator is the one I'm using to make the columns of the matrix S. Then we can take the equation A VL equal to A sub L VL, and we can say I0 on AL is I0 A, we just put in an identity in the form K0 identity matrix, K from 1 to n, and then we have the vector L, the inner product of the vector L, and that's just the sum K equals 1 to n of AIK, because of use that basis times SKL. But we know ace on L is just ace of LL, so this is also ace of L I0 L, or ace of L S I L. Okay. So now this matrix S is n by n. The columns are these vectors, and since the matrix is assumed to be non-defective, these column vectors are linearly independent, and consequently the determinant of S is non-zero. So S is non-singular. That means that it has an inverse. And since S has an inverse, we can multiply this equation by the inverse matrix, and then we get the sum. Sum I and K goes from 1. Let me write this I, K going from 1 to n, S inverse N I, A I K, S K L is then equal to the sum I equals 1 to n, ace of L, S inverse N I, S I L. So I'm basically on the left, I'm basically using the equation is this equals that multiplied by S inverse, and we get this. And this equation in matrix notation is S inverse AS equals A in diagonal form, that is to say the matrix A1, A2, AN. 0 is there. Okay, so that tells us that if you have a square non-defective matrix, you can diagonalize it by a what's called a similarity transformation. So this is called a similarity transformation. And so the bottom line then is that any non-defective matrix can be diagonalized by a similarity transformation. Another way of writing that is A is equal to S, AD, S inverse. So that's a pretty general result. Any questions? Yeah.
Are the only conditions on S that it has to have an inverse, or I mean,
S has an inverse because its columns are the eigenvectors of the matrix A, and A being non-defective has eigenvectors that are linearly independent. So the columns of S are linearly independent, and that means it can have a determinant that can't be 0. So it has an inverse. Okay, well the next topic is functions of matrices, and this of course is very important because of quantum mechanics and other fields. When you're dealing with matrices, you don't just have the matrix sitting there, but in quantum mechanics you take the matrix and you exponentiate it, you take the logarithm of the matrix, you do all sorts of things to the matrix with all sorts of functions, and consequently you need to know how to do that. And so here, let's suppose A, once again, A is a non-defective. It's funny how in mathematics we so often are forced to use negatives, like a non-abelian group, non-defective matrix. It's too bad we get in there and change the language around so that we would say A is a nice matrix, meaning non-defective, or one having linearly independent eigenvalues. Anyway, that's a slide. So suppose A is a non-defective invariant matrix. What do... Whoa! Yeah. Can you move back? Because I don't want to do this. Thank you. What sense do we make of a function of that matrix? And what I want to show you is that you can rewrite that, since we can always write A as SA diagonal, S inverse, we can rewrite this as S F of A diagonal, S inverse, where F of A diagonal is a diagonal matrix. There are serious outbreaks in this country and the world, this pandemic. So if you have the flu, stay home. In fact, even if you have a cold, stay home. Because colds are infectious too. And wash your hands a lot. And if you see something and it's wet and it's not yours, don't touch it. Okay, zeros elsewhere. All right, so this is the diagonal matrix. So this is a general rule, and in fact, if you think more generally in terms of linear operators acting on infinite dimensional vector spaces, this is how you think about it. This is certainly how I think about it. Namely, an arbitrary function of a linear operator is some operator, some similarity transformation to the diagonal matrix, and in the finite dimensional case it's this. So let's for the moment just focus on the finite dimensional case. But that's how we make sense of, that's how we define this, and how we compute it. This is the way one actually computes these things. All right, now let me show you why this definition makes sense. Here I'm supposing, or let us suppose, just by way of illustration, that this function f, after all, f is a function, and we're using as the variable not just the real variable x, but a matrix, and that f of x has a power series that spans from Cn x to the n. Then we'd expect f of a to be a sum n equals 0 to infinity, c sub n in a to the n. On the other hand, we can use this expression for a. So we say this is a sum n equals 0 to infinity, c sub n, s, a diagonal, s inverse, raised to the power n. Okay? All right. Now something magical happens. And to see it, let's just look at the second term. The second term in this would be S A diagonal S inverse squared. Well, that's going to be S A diagonal S inverse S A diagonal S inverse. Well, you see, since S inverse S is 1, this guy drops out. This is just equal to 1. And you can imagine putting a third S A diagonal S inverse here, then these guys would drop out. S inverse S would drop out. The result is that this thing is now equal to sum n equals 0 to infinity c sub n S A diagonal to the n S inverse. Okay?
Why are you squared there?
Oh, that's an example.
Okay.
All right. So in other words, what I'm using is this little rule: S A diagonal S inverse to the n equals S A diagonal to the n S inverse. Okay. So that means then, pulling the S out there, that we have f of A is equal to S sum n equals 0 to infinity c sub n a diagonal to the n S inverse. But on the other hand, what this thing is S sum n equals 0 to infinity c sub n. Now, a diagonal to the n is just a matrix a1 to the n, a2 to the n, a capital N to the n, zeros, S inverse. But then that is just f of a diagonal. And so this is S inverse f of a diagonal. S, not S inverse. Okay. So that's the result. In other words, f of a equals this. And that's what I proved over here, where f of a diagonal is just f of a moves down to f of a n. And because you see here, maybe I should have just added an extra step. So this thing is equal to S sum Cn a1 to the n sum Cn a2 to the n sum Cn an to the n zeros S inverse, which is that equal to this, which is that. Okay, is that all right? So this is basically what people have in mind when they form functions of matrices, which is of course what one does all the time in quantum mechanics. So is there a question here? Maybe I skipped something. Is that a question? All right, I got a couple of examples here. In quantum mechanics, quantum evolution.
That was a chunk.
They're all the same. All right. In quantum mechanics, well, that was yours.
Yeah.
I thought you wanted to plug it. No, no. The other thing is supposed to have. The time evolution operator in quantum mechanics is e to the minus I h t over h bar. So this is what we can call u of t. And actually, you know, if you move back about 6 inches, I'll be able to get it. Okay, now h here is the Hamiltonian. Named after Hamilton. In fact, his name is William Rowan Hamilton. 1805, 1865. H bar, a Planck constant over 2 pi. Although Hamilton only lived 60 years, Planck made it to something like 90 years, 89. Something like that. Anyway. And by the way, h bar is approximately 10 to the minus 34 joule seconds. Okay, so this Hamiltonian is Hermitian, and in particular, we'll see in a little while that the Hamiltonian is always, the Hermitian operators are always non-defective. And so use this approach. And so since it's non-defective, it can be diagonalized by a similarity transformation. And so the time evolution operator, U of t, which is minus I of t over h bar, is then the similarity transformation e to the minus I h diagonal t over h bar is inverse. And now this then is this exponential diagonal matrix is itself a diagonal matrix, and in particular it's S and then e to the minus I. The eigenvalues are normally we call them energies E sub n. Then this is e to the minus E n t over E1t over h bar, e to the minus I E2t over h bar down to e to the minus I and nt over h bar. Zeros elsewhere. And S inverse. Okay, so that's the way we look at that. And in particular, suppose we are dealing with a particularly simple system where we have three states, three energy levels. Then we can define the angular frequencies, omega I, as EI over h bar, and then this unitary time evolution operator will be the similarity transform of the diagonal matrix, e to the minus I omega 1t, e to the minus I omega 2t, e to the minus I omega 3t. 0, 0, 0, 0, 0, 0. S inverse. Okay. So that's the way we think of that's the way we compute the exponential of the matrix. One more example. Let's suppose we have a system described by a density operator rho. Then we can ask, well, what is the entropy of a system described by density operator rho? And the answer is the entropy S. All right, now this is unfortunate. I've been using S for a matrix that forms, that implements the similarity transformation, but the standard symbol for entropy is also S. So live with it. S is minus K times the trace of rho natural log of rho. K here is Boltzmann's constant, 1.38 roughly, 10 to the minus 23rd joules per degree Kelvin. And this is named after Ludwig Boltzmann, born in 1844 and committed suicide in 1906. I don't know what to say about that. Anyway, rho is Hermitian. This is just all density operators are Hermitian. They're a unit trace, and they're positive in this sense. The mean value of the density operator in any state psi is a non-negative number. This non-negative number, in fact, is the probability that the system described by the density operator rho is found to be in the state psi. Okay. Well, since rho is Hermitian, we can diagonalize it by a similarity transformation. We'll see later that that can be diagonalized by a unitary transformation. And so S then is equal to minus k trace, and now we have S row diagonal S inverse and S natural log row diagonal S inverse. And the trace goes like that. And now the trace, remember, trace of ABC is equal to the trace of BCA. Trace is cyclic, and consequently you can take this S inverse S just gives the identity matrix. You move this S to the end, you have again the identity matrix, and you bring the S over here. And so the entropy then is minus K trace of row diagonal log of row diagonal. And in particular, if we imagine a special case in which the density operator of the system has only 3 states, and then row diagonal might be row 1, row 2, row 3, then S would be minus K row 1 log row 1 plus row 2 log row 2 plus row 3 log row 3. And on the other hand, all the rows are less than 1, so the logs are negative, so you can rewrite that as K row 1 log 1 over row 1 plus row 2 log 1 over row 2 plus row 3 log. Okay, so that's row 1 is the probability that the system is in state 1, row 2 is the probability the system is state 2, row 3 probability the system is state 2. All right, so let's, I think this is a good place to pause and maybe do a demo, and but if there's a question about this, we can get it answered, or at least asked now. And you know, you can interrupt any time with questions. I'll be interrupted. And I'm not going to lose points for questions. Okay, ask me questions. Okay, well, let's see if I turn this on with a beam here. This, you might wonder, what is it? It's not a urine sample. This is a supersaturated solution of sugar in water, and I think the reason why it's, well, I don't really know this, but I think the reason why it is yellow is that I tried to get it last Wednesday dissolved quickly so that I could show it in the problem session, and I put it on a burner, and it would be, some of the sugar may have oxidized and turned color. All right, so let's see whether, first of all, this beam, no, it's going to be too low. Ah, good, okay. All right, so you can see the beam. Now, those of you in the back, if you want to just come up here and get a better view, there it is. Feel free to come up. Okay, this is a linear polarizer. Remember that the photons coming out are linearly polarized up, and so if I put this, if I put this linear polarizer in with the, boy, that is tight. Let me use a different one that I can turn these. That's nice. All right, so I put this in here, with the, so now this is just selecting again for polarized, plane polarized up. But if I start rotating it, it gets darker, you see. And if I rotate it all the way to horizontal, you can see that it just about goes out. Should I turn off the light? Would that be better? Or is it, what do you think? All right, so there's the, it's not completely extinguished, but it's, okay, now essentially nothing is getting through. Now this is sugar. Sugar, natural sugar, is composed of molecules that are not invariant, that change when you make a parity transformation. That is to say, if you take the molecule and then you flip, you consider the positions of all the nuclei, and you flip them from where they are through the origin to the opposite direction, where you multiply all the position vectors of all the nuclei by -1, and do the same to the electrons. You don't get, well, obviously you don't have the same thing, but you can't take that reflected one and rotate it back and get the original sugar molecule. So in other words, it's not invariant under what's called a parity transformation. Another way of saying that is it's a chiral molecule. And because it's chiral, the photons that are that have angular momentum in the direction of motion go through the different phase from those that have their angular momentum opposite the direction of motion. And so when plane polarized light goes through, which is basically the left circularly polarized, say, plus the right circularly polarized, once it goes through, it's then one phase times left circularly polarized plus another phase times right circularly polarized, and the result is it's no longer linearly polarized in the same direction, but it's changed by an angle. Okay, so let's see what happens. You see, it's almost extinguished. I put the sugar in, and amazingly enough, it gets brighter. And it gets brighter because the sugar has rotated the plane of polarization. And so some of it gets through. And now, to show what happens, how much do I have to rotate it to extinguish it again? Well, it's about that much. And now, I'm going to turn off the laser to show you this arrow. Well, not that you can see it very well, but yeah. All right, somebody here in the front will verify that the thing, instead of being horizontal, it's down like his pencil, and so I had to rotate it by about that much to extinguish it again. So that's the extent to which the something like 2 inches of the sugar solution was able to rotate the plane of polarization by about 30 degrees. All right, yeah.
That's depending on the density?
Yeah, sure. And in fact, this business of chiral molecules in natural systems, it's because, you know, natural systems evolved, and so when early cells found a way to make a sugar molecule, they did it with some huge protein, huge compared to the sugar molecule, and they found one that made the sugar, and so they kept it. And so all the enzymes that make the sugar molecule from whatever the precursors were, is basically evolved from that initial discovery by evolution, and so there wasn't any point in finding one that made the sugar molecule that was a chiral transform of the first one. It turns out, you know, there was that chemical called thalidomide that was a drug, and it was banned in the U.S. but in Europe and some other countries, other places, it was used. And the drug was made by a pharmaceutical company, and they made it with traditional organic chemistry methods. You add stuff into the beaker, heat it up, and so forth. And as a result, they made a combination that was 50% thalidomide with one chirality and 50% thalidomide with the other chirality. It turns out one of the chiralities is a useful drug. The other chirality is it's very dangerous for pregnant women and probably alters DNA in even people who aren't pregnant. So that's a certain chirality that you learn. Any questions? The amino acids, for example, that our proteins are made out of, there are 20 of them. 19 of them are chiral. Only one is non-chiral. Glycine. Anything else? All right. So in the problem session, we can play with this if you want, but we'll mainly concentrate on things relevant to mathematics. All right. So the next topic is Hermitian matrices. So linear operators that are Hermitian are represented by Hermitian matrices, and these Hermitian matrices have special properties, and I think you've probably all seen what these properties are, but let me tell you anyway, because some of you may not have, or some of you may have forgotten. Anyway, it's always nice to hear this again. So the matrix A is Hermitian. All right, so a square and the complex conjugate of its transpose is the matrix itself. So this is equal to A transpose complex conjugate. Right. Now, it's we're thinking that it's n by n, and so it has n eigenvectors with n eigenvalues. And so we have an is equal to a sub n. So we know from our previous discussion that the Hermitian operator will have n eigenvectors with n eigenvalues. Now our task then is to we'll show that these are linearly independent. They can be chosen to be orthonormal and therefore complete, and that the eigenvalues are real, which is one reason why we want the Hamiltonian to be Hermitian and the momentum to be Hermitian, the angular momentum to be Hermitian, because the values of the energy, the momentum, the angular momentum are real. Okay, well, let's take the Hermitian conjugate of that, and we'll get the equation n a dagger is equal to a n star n. And on the other hand, this is equal to n a, because a is Hermitian. So we have n a equals a star n. And now, if we just take the inner product of that, in fact, since we've got that equation, take the inner product of that with the state n, we get n a n equals a n star n n. But on the other hand, a on n is a sub n n, so this is also equal to a sub n n n. Well, this tells us then that a n star minus a n times n n is 0. And this is probably the first case where it matters that the inner product that we're talking about is the good kind, that is to say the Hermitian, or what was the other term, non-singular? In other words, because because the state n, this is a non-zero eigenvector, the inner product of n with itself is not 0. Consequently, we can divide by this, and we get a n star minus a n equals 0 are effectively an equals an, and of course not equals 0 then. So this says the eigenvalues are real of a Hermitian matrix are real. I'm sorry about my handwriting. But anyway, I've said it clearly, I hope. So the eigenvalues of the Hermitian matrix are real. All right, now, if I can reach high enough, I can use this space that's up here. Let's just take AM star on MN. This would be sort of practice in Dirac notation. This, of course, is the complex conjugate of AM times NM. And this AM is, of course, an eigenvalue of A, the one for the state M, and consequently we can rewrite that as N A M complex conjugate, because we have AM is A sub M N. And this is equal to M A dagger N, but A is Hermitian, so this is equal to M A N. And then N is an eigenvector of A with eigenvalue A sub N, so this is A sub N, N, N. So that very long equation tells us then that A sub M star minus A sub N on Mn equals 0. So let's remember how we derived this. We derived this by assuming that N was an eigenvector of A with eigenvalue A sub N, M was an eigenvector of A with eigenvalue A sub M, and we get this rule. On the other hand, we know that the eigenvalues are all real, so this is also equal to AM minus AN times Mn equals 0. All right, well, this tells us then that if A sub M is not equal to A sub N, then M and N are orthogonal. So that's what we've derived. So we have two eigenvectors of the Hermitian operator A. Then if the eigenvalues which are real are different, the eigenvectors have to be orthogonal. Now, for a generic Hermitian operator, you just look at the whole space of all n by n Hermitian matrices, so to say, n by n Hermitian matrices, and you just pick one at random. All the eigenvalues would be real, and they'd all be different. And so all the eigenvectors would be orthogonal. You could normalize them, the eigenvectors then would be orthonormal. Of course, especially in the sort of Hamiltonians that we use, that we like to use in physics, those are ones that have a lot of symmetry. And because they have a lot of symmetry, some of the eigenvalues are degenerate. For example, in the hydrogen atom, you have spherical symmetry. Also, there's a hidden symmetry, but never mind that. You have spherical symmetry, and so for the hydrogen atom, the energy levels depend upon the principal quantum number n, not the angular momentum L or the z component of the angular momentum m, or the quantum numbers that label the angular momentum L and the quantum number L that labels the angular momentum state, and the quantum number m that labels the orientation of the z component of the angular momentum. So in other words, the Hamiltonian for hydrogen atom is very, very degenerate. Instead of having, in its diagonal form, instead of having all the numbers different because of the symmetry under the rotations that take, rotate the, if you look at a proton from any direction, the electric field is the same if you're at the same distance from the proton. So, there's a great deal of degeneracy. The n equal 2 level has 4 states that have the same energy, not counting spin. If you count spin, there are 8 states that have the same energy. You go to the n equals 2 level, n equals 2 level, you then have not only L equals 1. Anyway, you have different values of L. I'm just doing that in my head, and I don't think I counted correctly. But as you go up, you have different values of L, and for each L, all 2L plus 1 values of M have the same energy. All the different L values have the same energy, and so you have a great deal of degeneracy. So degeneracy is a problem that we face in physics because we like to deal with simple systems, and simple systems have symmetry. And the hydrogen atom is a good example of that. An example where you don't have any degeneracy is, for example, a quantum oscillator. There, all the energy levels are different. They're equal to n plus a half h bar omega. There it is, non-degenerate. And those eigenvectors then are all normal. Okay, so what do we do when we have the case of degeneracy? Well, the first thing to say is that suppose we label the vectors for alpha in some set D, or in other words, alpha equal to 1 up to d sub n. In other words, suppose the degree of degeneracy for the nth level is d sub n, then there are n states there. Well, what you can notice is the A on a sum, alpha equals 1 to d sub n, c sub n, and alpha. This is any linear combination of these degenerate eigenvectors will be an eigenvector of A with eigenvalue A sub n of C sub n. That's C sub alpha. I should read these. I should look at my notes all the time. Okay, so alpha equals 1 to d sub n. So whatever the C's are, any non-trivial linear combination of states n alpha will be an eigenvector of the emission operator A with this real eigenvalue A sub n. So what we can do is we can then use the Gram-Schmidt process to make these things orthonormal. Okay. And so that's what we can do. The Gram-Schmidt procedure was worked out in equations of 179 and 191. Anyway, you can then normalize these. Well, the Gram-Schmidt will often normalize. Okay, but then two questions arise at this point. First of all, are these vectors, these n alphas, are these vectors linearly independent? And secondly, what linear combination should we choose? Because although Gram-Schmidt is a standard procedure, you turn the crank, you feed in the vectors, you turn the crank enough times, you get out an orthonormal set, provided the original ones were linearly independent. There are many other ways, in fact, infinitely many other ways, of forming an orthonormal set of vectors given a set of linearly independent vectors. You make all kinds of ones. And so there are two questions here. How to choose those coefficients, and why are these vectors linearly independent? And so let's just notice that if U is any unitary transformation or any unitary operator acting on this vector space, this n-dimensional vector space, then A on U n alpha is equal to, and I also want to say that A and U commute, which is AU minus UA equals 0. If that's true, then AU n alpha is UA n alpha, which is U A sub n sub alpha, which of course is A n U n alpha. So for any unitary, so you have these d vectors n sub alpha, you hit them with any unitary operator that commutes with U, and you get another set of eigenvectors with the same eigenvalues. And there are infinitely many unitary operators. So you have an enormous amount of choice here. The question is, how do you go about this in a sensible way? And we'll have to pick this up next time, but let me just give you the flavor of it. The flavor of it is you look for a crooked operator, one that doesn't have all the symmetry of the operator that you started with. And then you define A of epsilon as being A plus epsilon B. So B is this crooked operator. I should have used the C, I guess. Epsilon is a tiny real number. So this is still Hermitian. Now, because this is a crooked operator and you've broken all the symmetry, now the eigenvalues A sub n, which depend upon epsilon, in other words, A, the states n sub alpha comma epsilon will be A sub n of epsilon n sub alpha comma epsilon. So now this operator, this is A of epsilon. The operator A of epsilon, because it's so crooked, has n eigenvectors, of course, with n eigenvalues, but now all the eigenvalues are different because you've broken the symmetry. So since they're the eigenvectors of a Hermitian operator and the eigenvalues are all different, then these guys are all orthonormal. And so you can say n alpha epsilon, n alpha prime epsilon is equal to delta alpha alpha prime. You can take them orthonormal. And now you take the limit epsilon goes to 0. And this relation, since the right-hand side doesn't depend on epsilon, the vectors remain orthonormal, and A of epsilon goes to A. So in other words, this is a way of finding an orthonormal set of vectors, of resolving the degeneracy. And in fact, this is what one does in practice in quantum mechanical problems where you have a symmetry. And in fact, it's often true that the thing you add is some perturbation, we call it a perturbation, that breaks some of the symmetry. It might be a spin orbit coupling, or it might be a relativistic correction. There will be various ones to the hydrogen atom, and then you add the flying structure, the flying structure. Anyway, we'll pick this up next time. I'll hang around for questions.
Okay, so now I want to just click on this one.